So today what we're going to go over is comparing graphs and kind of more examples of what we did last time. We'll look at some histograms. We'll look at some box and whisker plots and kind of go through comparisons of them. Talk about skewness a little more. Hopefully get you a little more comfortable with each of them. So a lot of times when we have graphs, we'll have more than one graph so that we can compare the two graphs, because comparing two graphs is a whole lot easier visually to compare than two sets of data with just numbers. So we look at our first example here. It says it is almost always more interesting to compare groups. Histograms, we note the shapes, centers, and spreads of the two distributions. So what we have here is the number of days, spring versus summer, fall versus winter, and we're looking at the average wind speed during those days. So in the spring and summer, it looks like we had almost 50 days with an average wind speed of a little less than half a mile an hour, right? That's not a whole lot of wind, okay? Now our biggest day in the fall and winter was, we had about 35 days where the wind speed was over 2 miles an hour. So we're looking at those two graphs. One thing that automatically stands out to me is it's a lot more windy in the fall and winter than it is in the spring and summer, right? Something really easy to see from the visual. With the comparison, have a peak here below 2 miles per hour. Our peak here is above 2 miles an hour. Most of our data lies above that 2 mile an hour range. Most of our data here lies below 2 miles an hour. So definitely looks like the wind blows stronger during the spring and summer. You can also tell too, okay, here's 4 miles an hour. I guess that would be 6 miles an hour right here. So there were no data values over 6 miles an hour during the spring and summer. Here, we definitely had data value, at least one data value over 6 miles an hour here. So we had our fastest wind day during the fall and winter. So the distribution of wind speeds for the spring and summer months is unimodal and skewed to the right. That's something else we can talk about. So spring and summer, unimodal only has one peak. It's skewed to the right because my tail is pulled to the right. It says the distribution for the fall and winter months can also be considered unimodal. If you wanted to call it bimodal, I wouldn't have a problem with that either, because technically it does go up, go back down just a little bit, and then come back up. Sometimes for a single bar value, when it does this, sometimes we don't make so much big of a deal of it and call it unimodal. If you want to call it bimodal, you can. I still have not fixed my mouse, but there's slack. All right, when is the wind speed typically higher? We've answered that question. It's typically higher during the fall and the winter. But you can tell all that from your histograms, okay? All right, so pairing groups with box plots. So, all right, so here we have the same data, exact same data, but instead of comparing it with histograms, what we did is we compared it. Now we're doing it monthly, and we're doing it with box plots, okay? So we took each data for each month, and we put it in its own box plot, and we plotted them next to each other so we can kind of see what the wind does throughout the year, okay? So you read the little points there. It says box plots offer an ideal balance of information and simplicity, hiding the details when displaying the overall value or summary information. We often plot them side by side for groups or categories we wish to compare. What do these box plots tell you? I'm looking at them. It looks like, obviously, just like what we saw in the histogram. During the winter months, we got January, February, March. We got a lot higher wind speed than we do during the summer months, say June, July, August, right? So you can see there's a peak, it goes down, and then it seems to trend back up when it gets back towards the wintertime, fall time. Okay. What you can also tell in box plots that you cannot tell in histograms is we have some outliers. Okay. So I have an outlier here, here. I've got an outlier here. Got another one here, 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 here. So we've got quite a few outliers. Now, another interesting thing to note with these box plots, or box and whisker plots, is if you take an outlier for July, that outlier that we have identified for July is not an outlier for any of the other months, right? So that wind speed shows up in June or shows up in August, it's not an outlier. Does that make sense? So that's interesting because if I were to group, say, those clustered together, if I said winter, spring, fall, and summer, and I would have done that instead, that wouldn't have shown up as an outlier because it would have been grouped in with a couple other months. Okay, so sometimes you'll see outliers when you break it down into smaller groups. And something that's an outlier in something might not be an outlier in something else that's even just right next to it. So, other thing to note, a lot of times we want to know what the middle value is for the data. You can follow the middle or the median for all these data points. It's just the line that's right there in the middle. Some of these are skewed, some of them are not. So August would be skewed to the right because you have you have a long tail to the right. If you think about it, if you were to invert this, it would go this way. It wouldn't fall left, it would fall right. So you can call it skewed right or skewed to the high side. Let's see, I don't see one that's skewed to the left here. A lot of these are skewed right. That one would be skewed right. That would be skewed right. July, you might call that skewed right. It's kind of hard to tell because it's so small, but it would either be symmetric or skewed right. So you can tell skewness there too.
So would there ever be a situation that we need to know what the outliers are? And like, would I count July or would I not count July?
No, July, like you would consider, like you wouldn't throw out a whole month if that's what you're asking.
Right.
So you would keep July, and this outlier here, usually what I tell people is when you have an outlier, it really depends on what you're doing.
Okay.
If you have an outlier, I always go back and look at that outlier.
Okay.
If I have, let's say if I had July and this was an outlier, I'll go back to my handwritten notes and say, okay, was that really the number I was supposed to write it? Do I actually have that number? Because a lot of times when you're typing stuff in on the computer, you accidentally hit a button, you type in the wrong thing. And a lot of times you can correct it by that. You just go in, make a correction, you don't have an outlier anymore. If it is an actual value, you probably don't want to actually throw it out because it's significant, right? If we actually did have a really high wind speed day in July, that's something to note that, hey, every now and then we can get a really high wind speed day. You don't want to just throw it away. Sometimes you do, sometimes you don't. But it's not something you're going to do in this class. This class, you're basically worried about finding outliers. Okay. The only thing you'll have to know about an outlier, other than that, is that it's probably going to help pull my mean up. Does that make sense?
Yeah.
Okay. We were in another class where we were doing some coding and stuff. We might have to determine what to do once we reach an outlier situation, but here we're just mainly focused on finding them and going from there. So speaking more on outliers, outliers can arise for many different reasons. Common reasons include transcription errors, which I just talked about, misdocumentation, blocked or malfunctioning sensors, and truly different events. So my example here says, this was an example I dealt with when I was in grad school. We were doing field trials where we were measuring water clarity, and we had a whole bunch of sensors out on Lake Hartwell. And so it would be reading, it'd be reading, it'd be reading. One day we went out there, or one day we were watching the readings, and it was clear, 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 and then it went just like pitch black dark. And we couldn't figure out why. And we thought that our $3,000 sensor had gone bad, and the researchers were throwing a fit because it's a pretty expensive sensor. But before we went and bought a new sensor, we just took the boat and went out there, and all it was a leaf wrapped around the sensor. So sometimes your outliers can be caused by stupid stuff like that. So all we did was we cleared the sensor and we were good to go. So a lot of times it can be stuff as simple or as stupid as that. And if you were doing a technical research paper and you had an outlier, you don't want to, you could probably throw it out for a reason like that, but if you didn't want to, all you have to do is put in your notes, we had an outlying situation, it was corrected by clearing the sensor. So something as simple as that to make a note of why something like that happened. The other thing you can look at here, I got this graph of life expectancy in years. So these are all the different all the different countries and their life expectancy in years. If you look at it, all these different countries seem to follow a trend, but the USA is all over here by itself. a little bit lower than you would expect based upon how much we spend on our health per year. So it would be considered an outlier in this case. So a lot of times outliers are just outliers because they're outliers. There's nothing that was misdocumented or anything else. It just happened. Okay. Time plots. We don't really do a whole lot of time plots or time series in this class, but I want to show it to you one time. Time plots and time series are frequently used to track trends over time. While there might be a lot of point-to-point variation, sometimes you can smoothly estimate the general trends occurring over periods of time. In the example below, birth based upon years, you notice that birth drops to its lowest between 1970 and 1975. Doing an evaluation of why this may have dropped during those years, we can look back at the history and try to gather reasonable reasons why. Okay, so there's a lot of variation going on here, right? It's a lot of jumping. But what you'll notice is if you kind of took an average of where that's at, it increases, right? And then it starts to decrease, and then it increases again, and it drops. So you could kind of smooth out that curve, right? So there's going to be a lot of variation between, but there is a general trend upward here, right? That's the kind of stuff we try to gather in time series and time data. So this is used a lot like stock markets, right? Stock markets will trend and move all up and down, up and down, up and down. But sometimes they generally trend up, sometimes they generally trend down, sometimes they don't trend at all, right? They're just all over the place. And sometimes it looks like they're all over the place, but if you take a step back and look at it over a period of time, there is a general trend. Does that make sense? So time series is like a whole nother class. We don't teach it here. I took it at Clemson. It was a pretty cool class. But I don't think we offer it here. But this is pretty much all we cover with time series. Showing it to you, saying it's out there. If that's something you want to study in the future, you have to get set up in a program to do that. But in this particular example, it says perhaps, or we were looking at trying to figure out the trend here. So this is your, I believe it was birth rates, is what it is. So birth rates here, notice that from 1945 all the way up till a little after 1960 maybe, there's some increase, and then it starts to drop off. And then we have a steady increase, or a slight increase here, and then it kind of drops off again. So when we look at time series, a lot of the things we try to figure out is what happened at this particular period of time that caused an increasing thing to decrease. And sometimes we can pick out factors that cause that. Maybe there was a war, some natural catastrophe, food may have become scarce that caused birth rate to decrease, or maybe it was something like birth control had just come out, right? So you have all these births, but now people have birth control, they don't want to have as many kids, they start taking it, and the birth rate can decrease, right? Works the same way with your stock market and stuff. You can watch something increase and decrease. Maybe you see a factor happen that caused it to have some kind of influence in the past. Like, hey, last time this happened, this stock shot up. I just saw it happen again. Maybe I need to buy, right? Or maybe I need to sell. So that's kind of the whole idea behind using time plots or time series. Back to some kind of hard and fast number examples. We've already gone over the 5-number summary. We did that last time, but I will review. 5-number summary of the data set consists of the following: the minimum, first quartile, medium, third quartile, and the maximum. So it says the 5-number summary and IQR for organic tomatoes are. Basically what we have here is 2 data sets. We have a conventional leaf-room tomato plant yield and an organic tomato plant yield. So what I did, I actually farmed a decent bit still. And what I did one year is I wanted to see, okay, am I producing more tomatoes conventionally or organic? Using all that really expensive organic stuff really helped the actual tomatoes yield more. So I wanted to see if there was a significant difference here. So I think it was what? How many of these did I do? 2, 4, 6. I did 16. Actually did more than 16, but I just took readings on 16 plants each. And then I wanted to compare them. So let's do that real quick. We've got these 2 data sets. Let's put them in our calculator, figure out the 5-number summary, compare them, and then construct a box plot to kind of compare visually. I can see that y'all can set this up and do it yourself. Okay. So I'm going to pull out my TI as well, pull it up. So I've got my TI pulled up. Don't want to learn more. Put it here. That's not where I want it. I'm going to type in two lists. First list is going to be conventional. Second list is going to be organic. So if I go stat, edit, that's what's going to take me to a list. I'm going to clear my old list out by going to the top, hitting clear, and hitting enter. I'm just going to start typing these in. It doesn't matter which order you type them in, just make sure you don't type one list in the other list. Clearly messed one up. I messed 26 up, didn't I? Messed it up again. 14. What the devil? Alright, list 2, I'm going to make it organic. Hopefully y'all have already typed those in. It'll be easier for y'all, maybe. Okay, so I've got both my lists typed in. I'm going to find the five number summary for each. So I'm going to go stat, calculate one variable statistics. I'm going to go ahead and find it for list 1, which is my conventional list. So my conventional list here is actually listed second. So the minimum for my conventional is going to be, let's see, 11. My Q1 is going to be 15.5. My median, all you got to do is scroll down. Median is 20. My Q3 is 26. Max is 32. And my IQR is what? Yeah, Q3 minus Q1. So let's look at Q3 minus Q1. 26 minus 15.5. 10.5. So your IQR is 10.5. Remember, you got to do Q3 minus Q1 for your IQR. Okay. Now I already have my other list typed in, so I'm just going to hit stat, calculate one variable stat. And all I'm going to do is change the list that I have here. So to do that, I'm going to hit second stat or second list. I'm going to use L2. And then I'm going to hit calculate. And it does it for me too. So this is organic. It was the one on top. So organic min we found for it is going to be 8. Q1 is 17. Median here is 19.5. My Q3 is 22.5. My max here is 32. Okay, I gotta find my IQR. IQR is Q3 minus Q1. So my IQR is what? 5.5?
Yes.
Everybody good with finding those numbers? Okay. All right. The next part says construct a box plot for each group and compare the two distributions. Okay. So we've got everything almost that we need. We almost have everything we need for, trying to find a decent color, for comparing and computing or drawing the box plots. We've got the IQR, we've got Q1, Q3, and your median, which are your main points that you really need. If this thing jumps up one more time, we're gonna have a problem. Okay. So what's the one thing we have to do if we're gonna do out a box plot that we don't have yet?
Don't you have to do like your Q1 minus 1.5
Yeah.
times whatever?
So,
it is?
yeah, your outlier test is basically what it is. We're gonna test for outliers, which is your Q1 minus 1.5 IQR and your Q3 plus 1.5 IQR. Okay, so if I do that, Q1 here, we said was 17 minus 1.5. Our IQR here was 5.5. Okay. And then Q3, we did it. So Q3 is 22.5 plus 1.5, and our IQR here is 5.5. Let's see what kind of numbers we get with this. So if I pull my calculator back up, I'm going to do 17 minus 1.5 times 5.5. It should give me 8.75. All right. We'll do the other one, which is 22.5 plus 1.5 times 5.5. It gives me 30.75. Okay. So for organic, do we have any outliers?
Yeah.
Yeah. Right. So if I look at my lower cutoff, I'll have to click on this so we can see it. If I look at my lower cutoff for organic, my lower cutoff is 8.75. So if I go through here, is there anything less than 8.75 in my organic group? Yes, I have an 8. Okay, and I think that's the only one that's below. So we have a lower outlier. That's 8. How about upper?
Yes.
Yes, because our upper cutoff is 30.75, and I believe we got a 32, right? If you compare it to your mins here, my min was 8, my max was 32. You automatically know 8's one. You have to check, make sure that there aren't any others. Your max 32, so you know it's one. Check, make sure there's no others. We have an upper outlier at 32. So we have 2 outliers for our organic data. Easy enough so far? All right, let's do the same thing for conventional. So Q1 here. So for our lower boundary, we're going to do Q1, which is 15.5 minus 1.5 times your IQR, which is 10.5. And let's do your upper boundary. So our upper boundary is Q3, which is 26 plus 1.5 times 10.5. So let's figure out what these boundaries are. So 15.5 minus 1.5 times 10.5. So our lower boundary is negative 0.25. Our upper outlier boundary is 41.75. So do we have any outliers in the conventional data? No, we don't. Okay. All right. So if we bring it back around, I'm going to go ahead and write no outliers here. We need to construct the box plot for both, so it should be pretty easy at this point. I'm going to do it on the other one, try to move the camera with it. That'll work. Alright, so let's do them on the same graph. I'm going to do mine horizontally. You can do yours vertically if you wanted to, like we had the earlier example of it. And I'm going to do mine horizontally. I'm going to do, let's do organic on top and conventional on the bottom. So we'll do organic here. We'll do conventional there. Okay? So my lowest boundary, or my lowest number here is an 8, I think. My highest number is a 32. So I'm just going to go by 5s. So just got to create my lower axis there. Everybody good so far? If I start with my conventional data, I need to go ahead and plot my Q1, my median, and my Q3 as vertical bars. So my Q1 here is 17. 17 is about here. So I'll draw a vertical bar at 17. That's my Q1. My median here. My median is 19 and a half. So pretty close to 20. Good there, right? Okay. Q3 is 22.5. So about right there. And I'll connect those and make a box. Everybody good so far? This process is pretty easy. Now I gotta do my whiskers. Okay. So for organic, I have 2 outliers. I got a lower outlier at 8, upper outlier at 32. So we don't draw the whisker to the outliers. We draw the whisker to the point that's closest to our boundaries, which are here. So I'm not going to draw it to 8 because 8's cut off. Okay, so that means I'm going in for organic. I'm going to have to draw it at the next data point that's a little bit higher than 8, or 8.25, or 7.5. So what's our next data point?
15.
15? So I'll draw my whisker over to 15. Isn't very far at all. So here. So I've got my whisker here. Now on the other side, I can't draw it to 32 because 32 is an outlier. I need to draw it to something that's less than 30.75. So my next one, instead of 32, is 25. So I'll draw me a whisker over to 25. And then I have to plot my 2 outlying points. So I had an outlying point at 32. And I had an outlier point at 8. Easy enough. Everybody feel like they could do that on their own? If not, you got one more chance to watch because we're about to do conventional too, so we can compare. So, conventional, our Q1 for conventional is 15.5. So a little over 15, but not much. So Q1. Our median is going to be 20. So that's our median. Our Q3 is 26. Okay. Doesn't have to be perfect. Try to make it as good as you can. Okay, so I have the box for that. Right? Everybody good so far? Probably should have gone a little bit further over 26, but it's alright. Now I got to draw my whiskers on it. I don't have any outliers for my conventional data, so my whisker is going to get drawn all the way out to my min and all the way out to my max. Because I have no outliers. So 11 is my min, right there. My max here is 32. So about right here. 32 is like horribly here. Close enough. And I'm done. Right? What you got?
So for the first one, if we didn't have outliers, the whiskers would go all the way to
The endpoints, yeah. So if your min and max aren't outliers, just go ahead and you can draw your whiskers out to your min and max. If your min and max are outliers, you have to draw it to the next greatest point or lowest point, depending on if it's min or max. For your max, draw it to your next greatest point that's below the outlier boundary. Okay? And that outlier boundary is found by Q1 minus 1.5 IQR to Q3 plus 1.5 IQR. Does that make sense? And it's okay to have, like I said, 2 or 3 or 4 or 8 different outliers, depending on the problem. So here we had 2. If I'd have had another one here, let's say I'd have had another point that was cut off for that one, I believe it was 30 point something. So if I'd have had another point at 31, I'd needed to do that and plot it as well. Does that make sense? Okay. All right. So if we look at this, it says compare them. I'm looking at this, what I automatically see from the graph, the median on this one's a little bit larger than the median on this one. Q3 is larger than the Q3 here. Q1, this one's larger, but just barely. The whisker goes a lot further to the right on the conventional one than it does here, obviously. So if I was comparing my box plots, I would say that by comparing box plots, it looks like, one, because the median's larger, even if just barely, and the Q3 is larger, it looks like conventional did a little bit better than organic. I'm not gonna say it did, massively better, but just looking at these, this beats out this beats out this. Yeah, this does beat out this, but that's only 1 out of 3. This whisker beats out this whisker, even though I've got this outlier point. And this whisker is a little bit lower than this one, but you do have that outlier point to kind of offset that too. So if I give you 2 box plots to compare on a test or a quiz, it'll be pretty obvious which one's better than the other. Okay, I'm not going to make it really, really nitpicky. It'll be pretty obvious. So if everything's the same, like if Q1 and your median's the same, your whiskers are about the same, but your Q3 is bigger on this one than it is on this one, then obviously this one's bigger. Does that make sense? And if everything's the same, but your Q1's a little bit smaller on this one, obviously that's a smaller one, right? There's going to be something that pulls it to be smaller or bigger, but you should be able to kind of look through if you look at all those points. Hopefully that wasn't too difficult for you. Alright, so using that same data that we just did in box plots, I went ahead and made the histograms for them, so we didn't have to do both of them at the same class. We already made a histogram. So probably need to move the camera anyway. Computer telling me to do that. So we've got this histogram. You can kind of see that. So we've got these 2 histograms. We've got those 2 box plots. So it says, what advantages do the box plots of this data have over the histograms? Biggest advantage that a box plot has over a histogram, you can tell outliers in a box plot. You can't tell outliers from a histogram. You can tell what might be an outlier from a histogram, but you can't confirm it. You can confirm it with a box plot. Does that make sense? So here, I'm looking at this organic tomato one compared to this. It looks like this is probably an outlier. I can't confirm it, but it looks like it might be one. Here I can confirm it. Here, I probably wouldn't have listed this as an outlier. Here I can definitely tell it is one, right? So you can tell what is outliers by your box plot. You can't necessarily tell from your histogram. Okay. All right. What advantages do histograms of this data have over the box plots? Okay. The histogram, sometimes it's easier to see the distribution. So here if I'm looking at this, we've got, that would be unimodal. That one would be, you can make an argument for bimodal for that one, or you could even try to make an argument for uniform on that one if you wanted to. But the distribution is a little bit easier to see, in my opinion, with histograms. This particular example doesn't showcase it the best, but that would be my answer for that. The distribution can sometimes be easier to see with the histogram. Would it be practical to do a stem and leaf display to compare the distributions? Explain your answer. If I did a stem and leaf display, I would have a front of 0, 1, 2, and 3. So I would have at most 0, 1, 2, and 3. I'd have at most 4 bars on a stem and leaf plot. Here I would have, let's see, if you look at your data for this, here you would have 4 bars, here you would only have 3 because you start with a 1, you end with a 3. It would be 1, 2, 3. To me, it really wouldn't tell you much by putting it in a stem and leaf display. So I wouldn't use a stem and leaf display. Which plants typically produce more fruit according to the data? Appears that conventional tomatoes produce more fruit according to the data, but not by much. Okay, but not by much. So those would be a few questions I'd hope you'd be able to kind of go through. How do you describe, or how to describe a data set? Okay, so something you might be asked, you might be given a data set, you might be asked to describe it. If that's the case, we'll be looking for 4 things: the shape, the outliers, the center, and the spread. Okay. So the shape, it's either symmetric or roughly symmetric, skewed right, or skewed left. So those are pretty much the options you're going to have to go with. So is it symmetric, skewed right, skewed left? And I threw roughly symmetric in there because it doesn't have to be perfect. Outliers. You don't always have to have outliers, but if you do the 1.5 outlier criteria and find outliers, you need to say that you have either upper outliers or lower outliers, or both, or none. Okay, center. There are 2 choices for center. You can choose the mean or the median. Okay. If you chosen the shape to be symmetric and you don't have any outliers, then you must choose the mean as the center. Okay. Otherwise, you're going to pick the median. So if it's skewed, you pick the median. If it's skewed left, you pick the median. Skewed right, you pick the median. If it has an outlier, you pick the median. The only time you choose the mean is if it's perfect. It's symmetric with no outliers. Does that make sense? Spread, if you pick the mean, you must choose the standard deviation. Otherwise, choose IQR. IQR goes with median. Median, IQR. Mean, standard deviation go together. Does that make sense? So, if you give me mean here, you better choose standard deviation here. You give me median here, you better choose IQR here. Okay. Say all of your stuff in the descriptor. Say all of your description in context. Name the distribution you are selecting along with the units with the numbers, etc., etc. I don't need to add more than what we have. So I've got a little example to end on. It's pretty simple. So look at the following 3 distributions and describe the data set that they represent. So the first one, to describe the distribution in histograms below, match them to the box plots. So there's a matching one for each one of these. So this matches the one, this matches the one, this matches to another one. That's the first thing we're going to go through. We're going to match them, and then we're going to go through and we're going to do the shape, outliers, center, and spread. Show you how easy it is. Okay, so I'm looking at A, B, C. Okay, so I've got this histogram. Okay, it looks like you might consider it skewed right, you might consider it symmetric, but I do know it's unimodal, right? I also know it goes somewhere between a little less than 50 and a little more than 70. So which one does it line up with? 2, right? That's easy enough. B. B goes from 0 to 100. It is, and it's got a couple modes in there if you want to consider that, or you might consider it approximately symmetric if you cut it in half. But which one does it line up with? Lines up with 3. And easy. That means C has to line up with 1. So let's go through here and answer these. So the shape of A. Okay. Shape of A. Now the good thing about lining it up with the box plot first, if I look at A, you could probably make an argument for roughly symmetric here. If I look at the box plot that goes with it, which is number 2, right? It makes that argument for roughly symmetric a little bit stronger, right? Because your whisker here is about the same as your whisker here. your distance from Q1 to Q3, or your median to Q3 and your median to Q1 is about the same here. So I'm going to call it roughly symmetric. It doesn't have to be perfect. So A is roughly symmetric. Okay. I'm going to go ahead all the way through A, and then we'll get to B and C. So you'll have to kind of say, okay, A is this, A is that, A is that. So the other thing we want to know is outliers. So does A have any outliers? We know A lines up with number 2. And we see these little blue dots, which are outliers. So it has both outliers below and outliers above. That's how it looks like. Okay, so the other thing we're going to want to know, we've got shape outliers. If you scroll down, it also wants to know your center and spread, so I'm going to do those as well. Okay, so center, spread for A. If it is roughly symmetric, but it has outliers, I choose what? The median. Yep. If I choose the median for the center, I have to choose what for the spread? IQR. Okay. The reason I chose median is because it has outliers. If it has outliers, choose median. If it's skewed, choose median. It has to be perfectly symmetric, or it can be roughly symmetric, but it has to be symmetric with no outliers in order for it to be mean and standard deviation. Okay, easy enough? All right, let's do B. So B is this one and that one. So if I'm looking at this, symmetry doesn't mean it has to be perfectly bell-shaped. A lot of people confuse that. Symmetry just means you cut the thing in half and it approximately folds on each other. If I cut this thing in half here, it approximately folds on each other, right? It's not going to be perfect. But if I look at my box plot here, it really even more looks like it folds in half on each other. Like if I cut it right here at my median here, that would fold almost directly on top of that, right? So we're going to call this one symmetric. Okay. Does it have any outliers?
No.
No outliers. So I'm going to say no outliers. Okay. If it doesn't have any outliers and it's symmetric, what do I use as the center? Mean, right? It's the only case you use the mean. It has to be symmetric with no outliers. If I use the mean here, the spread here is going to be standard deviation. Okay. So we look at C. C is here. C is also here. C is what? We're looking at shape. C is skewed which direction? Right. So skewed right. We can easily tell that. We can easily tell that with the box plot, right? Because we have a really long tail to the right. Okay. You can also tell it with this. Our tail here is longer than it is here. It's closer to Q1 than it is Q3, and those have a lot of outliers, right? Which brings us to our next step. It does have outliers. The outliers are located where? On the upper side. Yeah, so we have upper outliers. So we got upper outliers. If we are skewed and have outliers, we're going to choose what for the center? The what?
Median.
The median. I choose the median for center, then I have to choose what for spread?
IQR.
IQR, which stands for interquartile range.
When do we choose the range for spread?
We don't.
Okay.
IQR is interquartile range. You're either going to choose IQR or you're going to choose standard deviation.
Okay.
IQR stands for interquartile range.
Okay.
That's why I said that. And that's it. Okay. Before you leave, though, I do have a little slight list of things that you might want to review before the quiz. Okay. So, take this. That guy there. So we will have a quiz next time. Like I said, chapters 1 through 4 is all we'll do. You'll come in, you'll take the quiz, and when you're done with the quiz, you can go home and enjoy your weekend. So things to review. Need to know the difference between quantitative versus qualitative. Okay. Quantitative deals with the quantities, qualitative deals with the qualities. It's pretty easy to go back and review that. The thing that we've been going over this whole last like 3 lectures is the different types of plots to use, okay? So you gotta know, I'm gonna do quantitative on this side, qualitative on this side. Okay. So the type of plot that I can use to describe quantitative data, types of plots. I can use a box plot, time plot, or time series, histogram, dot plot, and a stem and leaf. Qualitative, I can use a bar graph or a pie chart. Those are my 2 options that we've learned so far. Okay, so if I say, okay, what type of data is this? So this is qualitative data. And then the follow-up question is, what kind of plot or chart can I use to display this data? And you said it was qualitative, and you tell me a histogram, you're wrong, right? Okay. There's always a question like that I'll put on there. Okay, what type of data is this? It's quantitative. What kind of plot can I use to display this? Tell me bar graph, you're going to be wrong. All right, it needs to be a histogram. Okay. All right. What does it take to determine outliers? What 3 values do you need? IQR, Q1, and Q3. Yep, that's really all you need. Your IQR, your Q1, and your Q3. You have those 3 things, you calculate. Okay. You also need your data values to compare those 2. But really to calculate your fences, all you need is IQR, Q1, and Q3. Or you can use a box plot if you happen to have a picture of one. Okay. Remember that marginal distributions are for totals for the probabilities. They're found in the margins. That's pretty easy. Conditional distributions is for the subpopulation. Remember we went through that graph. No specific examples to do that. You know how to find your conditional distributions. Write that up here. If I give you a histogram and I ask you, does this data have outliers? And all you have is the histogram. Can you tell me? No. Okay. Okay. When do we use the mean and standard deviation? Symmetric with no outliers. Right? We use median and IQR, all the other times. Keep that in mind. Okay. Another question. See if you can put this together. I think I specifically said this at one point, or at least vaguely said this. But what % of the data is between Q1 and Q3? So you got your box plot, right? Got your whiskers. What's left of Q1? What % of the data? It cuts it into, median cuts the data in half. Q1 and Q3 cuts it into quarters, right? So 25% of your data is here, 25 here, 25 here, and 25 here. So what % of your data is between Q3 and Q1? 50. What % of your data is between your lowest number in Q3? 75, right? So you should be able to find this %. Okay. If I ask you, if I give you all this information and I say, okay, there's a data value that lies, okay. So this is your lowest point here, right? So this is your cutoff, this is your IQR, whatever. And the data point's here, it's an outlier, right? Would it be considered a very low value? Yes, right? An outlier is considered a very low value. So if I ask you, is a data point very low or very high? Determine whether or not it's an outlier. If it's an outlier, it is. If it's not an outlier, it's probably not. Does that make sense? Say, okay, you're given all this data. If I gave you another data point of, I don't know, 132, is that extremely high? Well, I'll do my outlier test. If I consider it an outlier, it's probably really high. If it's not an outlier, it's probably not that high. Okay, that's what we use as the criteria for now. Okay, and it'll be pretty obvious. You'll have data from like 0 to 10, and I'll give you like a negative number. Is that really low? Yeah, that's really low. Okay, because it's an outlier. Other than that, they'll kind of follow your homework a little bit. They follow some of the in-class questions. You should be okay for the most part. Do a little review. Other than that,